So now we have some logarithmic equations. So these equations will start with some aspect of a logarithm, and then it will be our job to still solve for that variable that we're looking for. Some of the answers may need a decimal equivalent, some may be exact. We'll see what we get when we try them. So we'll start off with A, which is log base 36 of x equals 1/2. And the way to think about that, questions such as this, is to realize that with that equal sign, we can rewrite this in a way that allows us to solve it. So remember that if you just focus on just the left-hand side, log base 36 of x, the answer to that is an exponent. It is saying 36 to what power gives us x. And we're being told, because of that equal sign, that the answer to that question is 1/2. That 36 to the 1/2 must equal x. So that allows us to take this and rewrite it as 36 to the 1/2 equals x. So those two things are equivalent. The equation up above and then the equation that we just rewrote. And now you can see, hopefully, that it's a very easy solve, because 36 to the 1/2 is the same as the square root of 36. And the square root of 36 is just 6. So then we have our answer. And that's all we had to do, was just rewrite it, which is great. For the second one, ln of x equals 4. Remember that, and I can write this, but remember we don't need to. Well, maybe I won't. So maybe I'll write it over on the side here, because I don't really want to write it because that's not how we write it. But remember that ln of x is just log base e of x. So although we don't write it as log base e because it's the natural log, that is what that is. And so what that means, though, is we can still do what we just did in the other one and just rewrite this. What the left-hand side is saying is e to what power gives us x. And we know by the equal sign that that is 4. So e to the 4, or the 4th power, equals x. And that's great, because that's our answer. We can go ahead and put that into the calculator, find your e and then do your exponent. And that's going to give you some decimal approximation, and we'll round that to 4 decimal places. So, yay. Okay, let me get that done. Here we go. Okay, so that's about, it's a big number, 54.5982. But we were able to get the answer in just one step by just using the rewriting, which of course allowed us to get the answer quite quickly. There we go. Okay, now notice, now take a look at why C is a little bit different than A and B. Our variable here is the base of the logarithm. It is the base of the logarithm. However, doesn't matter. All this is saying is x to what power gives us 5, and we're being told that the answer to that is 1/2. So x to the 1/2 equals 5. So I'm still just rewriting it. All you should notice is that it creates a slightly different equation of where the variable is. But it's actually something that we've seen before, or we should recognize, which is x to the 1/2 is the same as saying the square root. You don't need to write this, but just understand that that's the same. And that the way that we would free our x from that square root would be doing the opposite of square rooting, which is squaring. So we're going to square both sides. And we get x equals 25. So no need for the calculator there. Understand that what it's saying is log base 25 of 5 equals 1/2, and that is saying 25 to the 1/2 equals 5, which is true because that's the square root of 25. Over here, we have log base 4 of 3x plus 1 equals 2. So we see the variable is inside these parentheses, but again, we can use what the definition of log is to rewrite this. We want to free the variable from inside the logarithm. And the way to do that is just to use the fact that since a logarithm is an exponent, what the left-hand side is saying is 4 to what power gives us 3x plus 1? And we're told that that is 2, meaning 4 squared has to equal 3x plus 1. So it frees us from the logarithm. It also creates, as hopefully you can see, a basic linear equation that you know how to solve. So go ahead if you want, you can pause and solve that. So we'll subtract 1, we'll divide by 3, and we get x equals 5. It's always a good idea to check your answer. You can see pretty easily that if you plug in 5 here, that inside your logarithm is going to be 16. And so that's log base 4 of 16, which, since 4 squared is 16, the answer there is 2, and it checks out. Okay. Now we have examples with logarithms on both sides. And you might think, uh-oh, but don't think that. Because what is a rule that we have, what is something that is true, is if you have a log of something equaling a log of something and your bases are the same. So the key thing here is because the bases are the same, the only way for these two equations to be the same is if the insides are the same. So you'd have to have the same thing on the left-hand side that you have on the right-hand side, that these two things would have to be equal. So it allows us to really just take something that looks maybe challenging and understand that it's actually quite straightforward because of the fact that you have the same base on each one. Basic linear equation here, you can go ahead and solve it in your head if you want, even before I write it out. But we get x equaling 6. Again, this should be pretty easy to see because if you put 6 in the left-hand side, you get 13. And so you get log base 7 of 13 equals log base 7 of 13. Well, sure, those two things are equal. Something similar is occurring with f. So notice that you have log base 4, log base 4. And so you can set your insides equal to each other. You get x squared minus 16 equals 0. And you get, I'm going to factor these. Another way you could have done this problem is using the square root property. So I just want to put that out there. But I decided I'm going to bring the 16 and I'm going to factor it. So a couple different ways to do that. Because 16 factors, it's the difference of squares. That's why I decided to do that. But if you use the square root property, you get the same answers. So we get negative 4 and we get x equals positive 4. One thing I want you to remember is that we can't have a negative inside our logarithm. Even if we do something to it, it doesn't matter. If it is in any way in that logarithm negative, that is an issue with the domain. So in a case like this where we get two solutions, we're thinking, oh, maybe there's two solutions. There actually isn't two solutions because this negative 4 is not a valid solution. It would give us a negative inside, even that we square it, but before we square it, we have that negative inside the logarithm and we cannot put, it's not part of the domain of this logarithm to put in a negative 4. So we only have one solution in this case, which is just the positive 4. We really haven't been using that calculator too much. It's a nice number, that's all it is. All right, and then we'll have one more logarithm question here. Now this does have two logarithms, so you might be like, oh, maybe it's like what we just did. But, it also has this extra 2 on the right-hand side. So because of that, we can't just say that, x has to equal x plus 21 or anything like that, because it doesn't work because we don't have another logarithm. We can't use what we just did. But we can do other things. So in a case like this, you want to remember some of your properties of logarithms. It would be nice if we could rewrite this, but the two logarithms on the left-hand side don't allow us to do that yet. However, if we could combine them into one logarithm, we could rewrite this equation and make it into something that doesn't have a logarithm in it, so we could solve. What we want to remember is that product, quotient, and power rule that we have for logarithms. You can go back through your notes if you want and see those. But the product rule for logarithms says if you have logs in the same base here, if you have the logarithms with the same base and you have addition between them, you can combine them into one logarithm. This is going to be base 10, where the two insides are being multiplied. So we can write it like this, like that. So if you want, the idea here is that you can multiply them, and that's going to give you this. And then if you want, you can try to rewrite this. So now that we have this, we want to remember we have log, so that's just base 10. But now we have something that looks similar to what we just saw earlier in some of the other examples, where we just have log of something equaling a number. And so this is going to allow us to rewrite this, understanding that the left-hand side says 10 to what power gives us x squared plus 21x, and that the answer to that is 2, the squared, on the right-hand side that we see. So we can rewrite this using that fact that 10 squared equals x squared plus 21. Notice that this is quadratic because it has a highest degree of 2. We've seen some already that are linear, but this one is quadratic. So we have 100 equals x squared plus 21. We've solved quadratics already in some different ways. We've factored them. We've used the square root property. We've even used the quadratic formula. We've completed the square, a lot of different ways. But the first thing we do always try to do is say, could it factor? Because if it factors, then I don't have to do as much work as some of the other methods. So I'm going to bring the 100 to the other side. I'm going to look at this. And of course, I'm going to see, is there a possibility that it factors? I have to think about my factors of 100. Notice you're going to have one positive and one negative. That's the only way to get a positive middle and a negative at the end. You have to think about factors of 100. You have 1 times 100, 2 times 50, 3 times nothing, 4 times 25, 5 times 20, 6, no, 7, no, 8, no, 9, no, 10 times 10. Okay, and then of course we want either the addition or subtraction of those numbers to give us the 21. So we're going to be dealing with 4 and 25. Because the bigger one is positive, the 21, we want to use 25 and we want to use 4. So there you go. If you got that already, good job to you. And that's going to tell us that either x is negative 25 or x is positive 4. Now, very similar to what we just talked about, if we stick a negative 25 into this logarithm, we are now thinking about the fact that we have the log of a negative number and that is not valid, that is not part of our domain of logarithms in this way. And so we cannot use the negative 25 and we can only use the 4. So our answer again in this case just happens to be 4. But that's the idea behind a problem where you have a couple logarithms and then just a constant on the other side. And that is section 4.5.